What's the edge of our solar system? If you said Pluto, you're not alone. That's what most of us learned in school. But here's the thing. Beyond Pluto, way beyond the Kuiper Belt, there's this enormous region called the Oort Cloud. And when I say enormous, I mean it dwarfs everything else in our solar system. Today, I want to take you on a journey to this mysterious place. We're going to talk about how it formed, what's actually out there, and why scientists think it might hold some of the biggest secrets about our solar system's origins. This is going to be a deep dive we're talking about in narrated half of exploration because the Oort Cloud deserves that kind of attention. Some of this stuff genuinely sounds like science fiction, but I promise you, it's all based on real science. So if you're ready to have your mind expanded, let's get into it. And hey, if you end up enjoying this journey, I'd really appreciate a like. It helps more people discover these cosmic mysteries. Alright, so before we dive into the Oort Cloud, we need to understand where it actually is. Let's start with what we know. Most of us are familiar with the 8 planets, right? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. These worlds occupy what we call the planetary disk, a relatively flat plane, where the major bodies of our solar system orbit. Mercury, the closest planet to the Sun, sits at about 36 million miles away. Neptune, the most distant planet, orbits at roughly 2.8 billion miles from our star. Then there's Pluto. Poor Pluto got demoted from planet status in 2006, but it's still out there, orbiting at about 3.7 billion miles from the Sun. For decades, Pluto represented the edge of our solar system in the popular imagination. When New Horizons flew past Pluto in 2015, capturing those stunning images with its heart-shaped nitrogen ice plains, many people thought we were seeing the frontier of our cosmic neighborhood. But we weren't even close. In the 1990s, astronomers began discovering something remarkable. Beyond Neptune's orbit, there was an entire population of icy bodies we'd never known about. This region became known as the Kuiper Belt, named after Dutch-American astronomer Gerard Kuiper, who theorized its existence back in 1951. The Kuiper Belt extends from about Neptune's orbit 30 astronomical units from the Sun out to approximately 50 astronomical units. An astronomical unit, or O, is the distance from Earth to the Sun, about 93 million miles. So we're talking about a region that starts 2.8 billion miles from the Sun and extends to roughly 4.6 billion miles out. Now, this is already mind-boggling territory. The Kuiper Belt contains hundreds of thousands of icy objects larger than 60 miles across, and probably millions of smaller ones. Pluto is actually one of the largest known Kuiper Belt objects, along with other dwarf planets like Eris, Makemake, and Haumea. These are worlds of water ice, methane ice, and frozen nitrogen relics from the formation of our solar system that never got incorporated into planets. The Kuiper Belt was a major discovery. It fundamentally changed our understanding of the solar system's architecture. But here's where it gets wild. The Kuiper Belt isn't the edge either. Imagine standing at the edge of the Kuiper Belt, 50 astronomical units from the Sun. From this vantage point, the Sun would appear as just a very bright star, still the brightest object in the sky, but no longer the overwhelming presence we see from Earth. The planets would be invisible without a telescope. You'd be surrounded by icy bodies drifting in the darkness, occasional frozen worlds passing by on their ancient orbits. Now imagine traveling outward, not just a little farther, but 1,000 times farther, 10,000 times farther, 20,000 times farther. This is where the Oort Cloud begins. The Oort Cloud is a theoretical spherical shell of icy objects that surrounds our entire solar system. When I say theoretical, I don't mean scientists doubt it exists. The evidence is overwhelming. I mean we've never actually observed it directly. We can't. It's too far away, too dark, and the objects within it are too small and to spread out to see with current technology. But we know it's there because of what it sends us: comets. The Oort Cloud was first proposed in 1950 by Dutch astronomer Jan Oort, who was trying to solve a puzzle. Astronomers had observed certain comets with extremely long orbital periods, hundreds, thousands, even millions of years. These long-period comets seemed to come from all directions, not just from the plane of the solar system like the planets and Kuiper Belt objects. Their orbits suggested they originated from an enormous, roughly spherical region far beyond anything we'd previously imagined. Oort did the math. He calculated that there must be a vast reservoir of icy bodies extending from about 2,000 out to somewhere between 100,000 and 200,000 astronomical units from the Sun. To put that in perspective, the inner edge of the Oort Cloud is 40 times farther from the Sun than the Kuiper Belt, the outer edge. It extends nearly a third of the way to the nearest star. Let me give you a sense of the scale we're talking about. If Earth's orbit around the Sun 1 astronomical unit was the size of a quarter, then the Kuiper Belt would extend about 4 feet from that quarter. The Oort Cloud, it would stretch across to football fields. Light from the Sun takes about 8 minutes to reach Earth. It takes about 4 hours to reach Neptune. To reach the inner edge of the Oort Cloud, sunlight travels for nearly 12 days. To reach the outer edge, more than a year and a half. This is the true extent of our solar system. Everything we usually think of the planets, the asteroid belt, even the Kuiper Belt, all of it exists in a tiny bubble at the center of something vastly, almost incomprehensibly larger. Now, here's what makes the Oort Cloud so fascinating and so frustrating. We've never seen it. Not with the Hubble Space Telescope. Not with any of our most powerful ground-based observatories. Not with any spacecraft we've ever launched. The objects in the Oort Cloud are simply too small, too dark, and too far away. A typical Oort Cloud object might be a few miles across, maybe the size of a small mountain. It reflects very little light because it's made of dark, ancient ice and rock. And it's so far from the Sun that even what little light reaches it is incredibly dim. To understand just how challenging this is, consider this. The faintest objects the Hubble Space Telescope can detect are about magnitude 31. That's roughly 10 billion times fainter than what the human eye can see. An Oort Cloud object of reasonable size at the cloud's outer edge would be around magnitude 37 or 38. That's about 100 times too faint for even Hubble to detect. So how do we know the Oort Cloud exists? The answer lies in the comets that visit us. Every year, astronomers discover a handful of new long-period comets, icy visitors that swing through the inner solar system on orbits that take thousands or millions of years to complete. When we trace these orbits backward, they point to origins far beyond the Kuiper Belt, in the distant realm where the Oort Cloud should be. These comets are only direct evidence of the Oort Cloud. They're messengers from this distant frontier, kicked out of their ancient parking spots by gravitational disturbances and sent tumbling toward the Sun. When they enter the inner solar system, solar radiation heats their icy surfaces, creating the spectacular tails we associate with comets. But for billions of years, for their visits to the inner solar system, these objects sat frozen and dormant in the darkness of the Oort Cloud. Based on the number of long-period comets we observe, and accounting for how many we probably miss, astronomers estimate the Oort Cloud contains somewhere between 1 trillion and 2 trillion objects larger than half a mile across. 1 trillion, that's 1,000 billion. If you started counting these objects at 1 per second, it would take you more than 31,000 years to count them all. And here's the thing that really gets me. We're inside it right now. Earth, the Sun, all the planets were sitting in the center of this vast, spherical cloud of ancient ice. It surrounds us completely, in all directions, extending so far that its outer edge is loosely bound to the Sun's gravity, easily perturbed by passing stars. The Oort Cloud represents the final frontier of our solar system. It's the boundary where the Sun's influence fades and interstellar space begins. And despite being such a fundamental part of our cosmic neighborhood, it remains almost entirely unexplored and deeply mysterious. Before we continue, I'm curious, did you know about the Oort Cloud before watching this video? Let me know in the comments. I love hearing what you guys already know and what surprises you. Now, let's talk about how this mysterious region came to be. To understand the Oort Cloud, we need to rewind 4.6 billion years to the birth of our solar system. The story of the Oort Cloud is intimately connected to one of the most dramatic events in our solar system's history, the migration of the giant planets. Picture the early solar system. The Sun has just ignited, formed from the collapse of a giant molecular cloud. Surrounding this newborn star is a disk of gas and dust called the protoplanetary disk. Within this disk, small particles stick together, gradually building up into larger and larger bodies. Over a few million years, these growing bodies sweep up material in their orbits, eventually forming the planets we know today. But here's what's crucial. The planets didn't form where they are now. They formed closer together, in a more compact configuration. Jupiter, The giant of our solar system, with 318 times Earth's mass, probably formed somewhere between 3.5 and 5 astronomical units from the Sun, much closer than its current position at 5.20. Saturn, Uranus, and Neptune were also closer in, possibly in a more tightly packed arrangement. So what happened? How did they move? The answer lies in a process called planetary migration. As the young planets orbited through the protoplanetary disk, they gravitationally interacted with the material around them. These interactions created a complex dance of forces. When a planet encounters material orbiting closer to the Sun than itself, it gains angular momentum and moves slightly outward. When it encounters material farther from the Sun, it loses angular momentum and moves inward. For the giant planets, this process was dramatic and violent. Jupiter, being the most massive, had the most influence. As it interacted with the remaining planetesimals, the rocky and icy building blocks of planets, it generally migrated inward slightly. But here's where it gets interesting. While Jupiter moved inward, Saturn, Uranus, and Neptune moved outward. Think about what this means. These massive worlds, each containing more mass than all the rocky planets combined, were plowing through a population of billions or trillions of smaller icy bodies. It was like cosmic billiards on an unimaginable scale. Most of these encounters were violent. A small icy planetesimal, happily orbiting in the early solar system, would suddenly find itself in the vicinity of a giant planet. The planet's gravity would accelerate it to tremendous speeds, often flinging it completely out of the solar system or sending it on a highly eccentric orbit. Some planetesimals were thrown inward, possibly contributing to events like the late heavy bombardment that scarred the inner solar system about 4 billion years ago. Others were thrown outward. It's these outward thrown planetesimals that concern us. When a small object has a close encounter with a giant planet moving outward, it can be flung to enormous distances. Not quite fast enough to escape the Sun's gravity entirely, but fast enough to reach regions thousands or tens of thousands of away. These objects become Oort Cloud. Computer simulations of this process are remarkable. When scientists model the early solar system with realistic numbers of planetesimals and simulate planetary migration, they see exactly what we'd expect for Oort Cloud formation. Objects get scattered outward in all directions, eventually forming a roughly spherical shell around the solar system. The inner part of this shell, what we call the Hills cloud or inner Oort cloud, forms first, populated by objects that didn't get quite enough energy to reach the most distant regions. The outer Oort cloud forms from objects that had the most energetic encounters, reaching distances where the Sun's gravity is barely stronger than the gravitational influence of passing stars and the galaxy itself. Here's what really strikes me about this. Every object in the Oort cloud started its life in the inner solar system. That frozen comet nucleus sitting 50,000 astronomical units from the Sun. It might have formed in the region between Jupiter and Neptune, where water ice was stable in the young solar system. It might have orbited peacefully for a few million years if for a chance encounter with Neptune sent it on a million-year journey outward. That the story of the Oort cloud's formation is even more complex and more fascinating than just planetary migration. To fully understand it, we need to zoom out and consider where our Sun itself came from. Stars don't form in isolation. They're born in giant molecular clouds, vast regions of cold gas and dust where gravity can overcome the pressure that normally keeps these clouds to fuse. When a portion of a molecular cloud becomes dense enough, it collapses, fragmenting into hundreds or thousands of individual protostars, each surrounded by its own protoplanetary disk. Our Sun formed in such a stellar nursery, probably containing thousands of stars packed much more tightly than stars are in our current galactic neighborhood. Imagine dozens or hundreds of stars within just a few light years of each other, all young, all surrounded by disks of planet-forming material. In this environment, close encounters between stars would have been common. A star passing within a few thousand of our young Sun would have had dramatic effects on the developing Oort cloud. Its gravity could strip away loosely bound objects from our Sun's influence, or conversely, it could have deposited its own loosely bound objects into our solar system. This leads to a mind-bending possibility. Some of the objects in our Oort cloud might not be ours. They might have originated in the protoplanetary disks of our Sun sibling stars that formed in the same molecular cloud but have long since dispersed into the galaxy. Think about what this means. Out there in the Oort cloud, 50,000 or 100,000 though from the Sun, there might be icy bodies that formed around a completely different star. They'd still orbit our Sun. They've been gravitationally bound to it for 4.6 billion years, but their chemical composition, their isotopic ratios, the specific mixture of ices and rocks they contain, might tell a story of a different stellar environment. We have no way to test this yet. We haven't sampled Oort Cloud material to analyze its composition in detail. But it's one of the tantalizing possibilities that the Oort Cloud represents a potential archive not just of our own solar system's history, but of the stellar nursery where the Sun was born. There's another aspect to the birth nursery hypothesis that's worth considering. In a dense stellar environment, the Oort Cloud itself might have formed differently. Close stellar encounters could have populated the outer Oort Cloud more quickly and efficiently, and planetary scattering alone. These encounters might explain why the Oort Cloud extends so far out to distances where the Sun's gravity is incredibly weak. Some researchers have even suggested that the very outer reaches of the Oort Cloud, beyond 100,000 astronomical units, might be more densely populated than we'd expect from planetary scattering alone, precisely because of these early stellar encounters. If true, this would mean the Oort Cloud contains even more objects than current estimates suggest, perhaps several trillion rather than 1 trillion. Here's something I find deeply poetic about this. The Oort Cloud is a time capsule. The objects within it have been in deep freeze for 4.6 billion years, barely altered since the dawn of the solar system. They preserve information about the conditions, the chemistry, and the environment of the protoplanetary disk. They might even preserve information about our Sun's birth environment and its long-lost stellar siblings. On Earth, we study ancient history through archaeology, excavating artifacts that are thousands of years old. In geology, we study rocks that are millions or even billions of years old. But the Oort Cloud, it's an archaeological site frozen at the moment of its creation, 4.6 billion years ago. Every object there is a pristine sample of the material that built our solar system. Someday, maybe not in our lifetimes, but someday we'll send missions to the Oort Cloud. We'll retrieve samples and bring them back to Earth for analysis. When that day comes, we'll be holding in our hands the raw material of creation, unchanged since the solar system's birth. We'll be able to read the chemical signatures of the protoplanetary disk, understand the exact conditions that led to planet formation, and maybe even identify which objects came from other stellar systems. This brings us to one of the most intriguing aspects of Oort Cloud formation, the possibility of interstellar capture. We've talked about how objects from other stars, our Sun's birth cluster, might have been exchanged between stellar systems. But there's an even more exotic possibility. Objects from completely unrelated stellar systems might have been captured into our Oort Cloud over the billions of years since the Sun left its birth cluster. To understand how this could happen, we need to think about what interstellar space really is. We tend to think of it as empty, and by human standards, it nearly is. But nearly empty isn't the same as completely empty. Between the stars, there are clouds of gas, dust particles, and yes, occasionally, solid objects. When a star system forms, not everything gets incorporated into planets or stellar orbits. Some material gets ejected entirely, becoming free-floating interstellar objects. These could be rocky bodies, icy bodies, or even rogue planets, worlds that formed around a star, but were kicked out of their home system by gravitational interactions. Recent estimates suggest that interstellar space might contain trillions upon trillions of these objects. Most are probably small boulder-sized to mountain-sized chunks of rock and ice. But some could be much larger, planet-sized, even. Now, here's where it gets interesting. The Oort Cloud, especially its outer reaches, is very loosely bound to the Sun. Objects there orbit so slowly and so far from the Sun that they're vulnerable to gravitational perturbations. If an interstellar object happened to pass through the outer solar system at just the right velocity and trajectory, it could potentially be captured into a solar orbit, becoming part of the Oort Cloud. How likely is this? The honest answer is we don't really know. The probability of any given interstellar object being captured is very low. The object would need to lose just the right amount of energy, probably through a gravitational interaction with one of the giant planets or a lucky encounter with another solar system object. But over 4.6 billion years, with potentially large numbers of interstellar objects passing through our region of space, It's quite possible that dozens, hundreds, or even thousands of captured interstellar objects now reside in the Oort Cloud. In 2017, we got our first confirmed detection of an interstellar object passing through our solar system. Named Oumuamua, this object had a hyperbolic trajectory, meaning it was moving fast enough to escape the sun's gravity and was just passing through. Its discovery was groundbreaking because it proved that interstellar objects do indeed wander between the stars and occasionally pass through our solar system. 2 years later, in 2019, we detected a second one, Comet 2I, Borisov. Unlike Oumuamua, which was rocky or possibly even metallic, Borisov looked like a comet, complete with a tail of gas and dust. This told us that icy interstellar objects exist and can survive the journey between the stars. These detections have revolutionized our thinking. If we can detect 2 interstellar objects passing through the inner solar system in just a few years of looking, there must be many, many more out there. Some researchers now estimate that interstellar objects might pass through the inner solar system every year or 2. We just haven't been looking carefully enough to spot them all. Now, imagine the outer Oort cloud. It's much larger than the inner solar system, with a much bigger cross-sectional area for capturing objects. If interstellar objects are common, then over billions of years, quite a few might have been captured out there. What would this mean? It would mean the Oort cloud is even more diverse than we thought. Most objects would still be native to our solar system, scatter upward by planetary migration. But sprinkled among them might be visitors from across the galaxy. Some might come from stellar systems hundreds of light years away. Some might come from very different types of stars, red dwarfs, which are much cooler than our sun, or hot blue giants, or even stars with different chemical compositions because they formed at different times in galactic history. Each of these objects would tell a different story. By analyzing their composition, their mixture of ices, the ratios of different isotopes, the organic compounds they contain, we could learn about planet formation around other types of stars. We could understand how chemistry varies across the galaxy. We could even look for biosignatures, though I want to be clear, the probability of finding anything biological on these objects is extraordinarily low, but the possibility exists. Here's something that really captures my imagination. If interstellar objects can be captured into our Oort cloud, then the reverse is also true. Objects from our Oort cloud can be ejected into interstellar space. Over the lifetime of our solar system, gravitational perturbations from passing stars have probably ejected millions or billions of objects from the Oort cloud, sending them wandering through the galaxy. Some of these objects might travel for millions of years before encountering another star system. A few might be captured into those systems, becoming part of other stars or clouds. In a sense, star systems exchange material not directly, but through this slow, random process of ejection and capture over cosmic timescales. This means that somewhere out there, orbiting another star, there might be an object that originated in our solar system. An icy body that formed between Jupiter and Neptune 4.6 billion years ago, got scattered outward, spent a few billion years, our Oort cloud, and was then ejected by a passing star. It's now part of someone else's cosmic neighborhood. And somewhere in our Oort cloud, there might be an object with a similar history, but in reverse. It formed around another star, was ejected, wandered through interstellar space, and found a home in our solar system. We are, in a very real sense, connected to the rest of the galaxy through the Oort cloud. Now let's talk about what we actually know is in the Oort cloud. The primary evidence comes from the comets that visit us, those spectacular objects that occasionally light up our skies with their glowing tails. Comets are often described as dirty snowballs, though that's a bit of an oversimplification. A more accurate description would be icy bodies composed of frozen water, carbon dioxide, methane, and ammonia, mixed with dust, rocky particles, and organic compounds. The nucleus of a typical comet, the solid part, might be anywhere from a few hundred meters to tens of kilometers across. For most of their existence, comets in the Oort cloud are completely frozen and inert. At distances of thousands or tens of thousands of from the Sun, temperatures hover just a few degrees above absolute zero, around -270 degrees Celsius. At these temperatures, everything is frozen solid. Water ice is as hard as rock. Even gases that are normally difficult to freeze, like carbon monoxide, are solid. These objects can sit in these frozen orbits for billions of years, never changing, never warming, preserved exactly as they were when they formed. But occasionally, something disturbs them. The most common disturbance comes from passing stars. Our Sun isn't alone in its journey through the galaxy. Other stars move past us at various distances, and occasionally, maybe every few million years, a star passes close enough to gravitationally perturb objects in the outer Oort cloud. When this happens, objects that were in stable circular orbits can have their orbits altered. A gentle gravitational tug, accumulated over the weeks or months that a star takes to pass by, can change a nearly circular orbit into an elongated ellipse. If the perturbation is just right, the new orbit will bring the object much closer to the Sun, close enough that solar radiation begins to have an effect. This is how long-period comets are born. As an Oort cloud object falls inward on its new orbit, it takes thousands or even millions of years to complete the journey. The gravity of the planets, especially Jupiter, can further alter its path. Eventually, if the orbit brings it close enough to the Sun, typically within a few hours, something remarkable happens. Solar radiation begins to heat the comet's surface. Ices that have been frozen for billions of years begin to sublimate, transitioning directly from solid to gas without melting. This gas carries dust particles with it, creating a cloud around the nucleus called a coma. The solar wind, a constant stream of charged particles from the Sun, pushes its gas and dust outward, creating the characteristic tail that points away from the Sun. Some of these comets are spectacular. Comet Hale-Bopp, which visited the inner solar system in 1997, was visible to the naked eye for 18 months, longer than any comet in recorded history. Its nucleus was estimated at 60 kilometers across, and its tail stretched across millions of kilometers of space. Hale-Bopp came from the Oort cloud, on an orbit that takes about 2,500 years to complete. Comet Hyakutake, which passed by Earth in 1996, had a tail that stretched 570 million kilometers, nearly making it the longest cometary tail ever observed. It too came from the Oort cloud. But here's what's fascinating. These spectacular visitors represent only a tiny fraction of the Oort cloud's population. Most Oort cloud objects never get perturbed into the inner solar system. They remain in their distant orbits, frozen and invisible, for the entire lifetime of the solar system. The comets we do see give us valuable information. By studying their composition, we learn about the chemistry of the early solar system. Comets are rich in water ice, but they also contain more exotic ices: frozen carbon dioxide, carbon monoxide, methane, ammonia. They contain complex organic molecules, compounds containing carbon, that are the building blocks of life as we know it. In fact, some scientists think comets might have played a crucial role in the origin of life on Earth. During the late heavy bombardment, about 4 billion years ago, Earth was struck by numerous comets and asteroids. These impacts might have delivered water to Earth's surface, filling the oceans. They also delivered organic compounds, the raw materials for life. If this hypothesis is correct, then the Oort cloud isn't just a distant curiosity. It's intimately connected to our existence. The water in your body, the organic molecules that make up your cells, some of them might have originated in the Oort cloud, delivered to Earth billions of years ago by cometary impacts. There's another aspect of long-period comets worth mentioning. They're incredibly difficult to predict, because they come from such great distances and we typically don't see them until they're already on their way in. We often have only months or years of warning before a new long-period comet arrives. Some of these comets make spectacular shows, like Hale-Bopp. Others disappoint, appearing much fainter than predicted. This is because cometary activity depends on complex factors: the exact composition of the nucleus, whether volatile ices are exposed on the surface, how the comet's rotation affects gas emission, and more. Some comets break apart under the stress of their close approach to the Sun. The nucleus, held together by ice that's been frozen for billions of years, suddenly heats up and experiences enormous thermal stress. It can fracture, split, or completely disintegrate. Comet Shoemaker-Levy 9, which famously crashed into Jupiter in 1994, had broken into more than 20 pieces before its impact, probably due to a close pass by Jupiter a few years earlier. Other comets survive their close approach but have their orbits drastically altered by planetary gravity, especially Jupiter's. A comet that came from the Oort cloud on a million-year orbit might end up on a much shorter orbit after passing through the inner solar system, essentially becoming captured into a Jupiter family orbit. These comets, which now return every few years or decades, have lost their connection to the Oort Cloud. Every year, astronomers discover a handful of new long-period comets. Most are faint, only visible with telescopes, but occasionally we get lucky. A bright comet appears, visible to the naked eye, reminding us of the vast reservoir of icy bodies that surrounds our solar system. Each of these visitors is a messenger from the deep freeze of space, carrying information about conditions 4.6 billion years ago, offering clues about how our solar system formed and evolved. The comets aren't the only thing in the Oort Cloud. The sheer volume of this region, and that's what we need to grasp first, suggests the possibility of much larger objects. Let's talk about the volume we're discussing. The Oort Cloud is roughly spherical, extending from perhaps 2,000 to 100,000 astronomical units or more from the Sun. If we calculate the volume of this spherical shell, we get a number that's difficult to even conceptualize, roughly 1,014 cubic. That's 100 trillion cubic astronomical units of space. To put this in perspective, the volume of space occupied by the 8 planets' orbits from Mercury out to Neptune is about 10,000 cubic AU. The Oort Cloud is 10 billion times larger. Now, we think the Oort Cloud contains about 1 trillion objects larger than half a mile across. That sounds like a lot, but spread across that enormous volume, it means each object has, on average, about 100,000 cubic of space to itself. These objects are extraordinarily sparse. The Oort Cloud is far emptier than the emptiest vacuum we can create in a laboratory. But here's the thing, 1 trillion is probably an underestimate, and it only counts objects larger than half a mile. There are almost certainly many more smaller objects, and statistically speaking, in such a large population, there should be larger objects too. Size distributions in astronomical populations typically follow what's called a power law. For every object of a certain size, there are several more objects half that size, and many more objects half that size again. This pattern continues both upward and downward from any reference size. If we apply this kind of distribution to the Oort Cloud and work our way up in size, we should expect not just comet-sized objects, but larger ones too. How large? Well, that's the question. In the Kuiper Belt, we've found objects ranging from tiny pebbles up to Pluto, which is 2,377 kilometers in diameter. We've found several other dwarf planets in the Kuiper Belt with diameters over 1,000 kilometers. If the same size distribution applies to the Oort Cloud, and there's no particular reason to think it wouldn't, then there should be dwarf planet-sized objects out there. We just haven't found them yet, and here's why. They're too far away and too dark to see. Remember, the objects in the Oort Cloud are visible only by reflected sunlight. But sunlight dims with the square of distance. An object at 50,000 astronomical units receives 2.5 million times less sunlight than an object at 1 astronomical unit, and the reflected light has to travel back to us, dimming by another factor based on distance. The result is that even a fairly large object, say, something the size of Pluto, would be incredibly faint if it were in the Oort Cloud. Our best telescopes could detect a Pluto-sized object in the inner Oort Cloud, maybe out to a few thousand O. Beyond that, even dwarf planets become effectively invisible to us. In the outer Oort Cloud, you could have objects the size of Mars, and we wouldn't be able to see them. This raises an intriguing possibility. There might be a hidden population of large objects in the Oort Cloud. Some researchers have even speculated about the existence of what they call Planet 9, a hypothetical planet several times the mass of Earth, orbiting in the distant reaches of the solar system. The Planet 9 hypothesis was proposed in 2016 by astronomers Konstantin Batygin and Mike Brown. They noticed something odd about the orbits of several distant Kuiper Belt objects, the most distant ones we've found, with orbits that take them far beyond Neptune. These objects' orbits seemed to be clustered in a way that was statistically unusual. They all had similar orbital orientations and similar perihelion argument-technical terms that described the shape and orientation of their orbits. This clustering could be random chance, but the odds of it happening naturally are fairly low, maybe a few percent. A more likely explanation, Batygin and Brown argue, is that there's an unseen planet out there, perhaps 5 to 10 times Earth's mass, orbiting at a few hundred O from the Sun. The gravity of this planet would shepherd these distant objects into similar orbits, creating the clustering pattern we observe. Now, I want to be clear about something. Planet 9 is hypothetical, it hasn't been directly observed. The evidence is circumstantial, based on the orbital patterns of other objects. Many astronomers are searching for it, and if it exists, they'll probably find it eventually, but as of now, it remains speculative. However, the broader point stands. There could be large objects in the distant solar system that we simply haven't detected yet. Whether or not Planet 9 specifically exists, the vastness of the Oort Cloud makes it plausible that undiscovered dwarf planets or even larger bodies lurk out there. What would these objects be like? Well, they'd be frozen worlds, far colder than any place in the inner solar system. Surface temperatures would be just a few degrees above absolute zero. Any atmosphere it once had would have frozen onto the surface billions of years ago. They'd be dark, reflecting very little of the feeble sunlight that reaches them. From their surfaces, the sun would appear as just a bright star, and the sky would be filled with stars that never move because at those distances, orbital motion is so slow that the stars would appear essentially fixed over human timescales. These worlds would be ancient and pristine, virtually unchanged since their formation. They'd be time capsules, in the truest sense frozen snapshots of the early solar system. Studying them would be like opening a window into the past, into the conditions and processes that led to the formation of the planets, including Earth. This seems like a good time to talk about how close we've actually come to the Oort Cloud. The answer might surprise you. Not very close at all. The farthest human-made objects from Earth are the Voyager 1 and Voyager 2 spacecraft. Launched in 1977, these twin probes conducted a grand tour of the outer solar system, visiting Jupiter, Saturn, Uranus, and Neptune before heading out into interstellar space. Voyager 1 is currently the most distant. As of 2024, it's about 165 astronomical units from the Sun, traveling at roughly 3.6 astronomical units per year. That might sound fast, but let's put it in perspective. Voyager 1 has been traveling for 47 years. It's covered 165 astronomical units in nearly half a century. The inner edge of the Oort Cloud is at about 2,000 astronomical units. At its current speed, Voyager 1 will take approximately 300 years to reach the inner edge of the Oort Cloud. 300 years. The spacecraft that left Earth when Jimmy Carter was president won't reach the Oort Cloud until around the year 2300, and that's just the inner edge. To reach the middle of the Oort Cloud, at perhaps 50,000 astronomical units, would take Voyager 1 about 14,000 years at its current speed. To reach the outer edge, at 100,000 astronomical units, would take nearly 28,000 years. By that time, Voyager 1 will be long dead. The spacecraft is powered by radioisotope thermoelectric generators, basically nuclear batteries that convert heat from decaying plutonium into electricity. These generators lose power over time as the plutonium decays. NASA estimates that Voyager 1's instruments will run out of power sometime around 2025, literally within the next year or two. After that, the spacecraft will continue its journey in silence, a dead hulk drifting through space, but we won't receive any more data from it. Voyager 1 will pass through the Oort Cloud as an inert artifact, a monument to human exploration. But it won't be able to tell us anything about what it encounters there. Voyager 2 is in a similar situation. It's currently about 138 astronomical units from the Sun, traveling at about 3.3 astronomical units per year. It too will enter the Oort Cloud in a few centuries, and it too will be powered down long before then. These spacecraft represent the extent of human reach into space. They're the farthest we've sent our technology, and they've only just barely left the immediate neighborhood of the Sun. The Oort Cloud remains utterly unexplored, not just unvisited but fundamentally beyond our current reach. Here's something that really drives this home. The light travel time to Voyager 1 is currently about 23 hours. That means a signal from Earth takes 23 hours to reach the spacecraft, and the spacecraft's reply takes another 23 hours to reach us. A round-trip communication takes 46 hours, nearly 2 full days. Now imagine communicating with a spacecraft in the Oort Cloud. At 50,000 astronomical units, the light travel time would be about 290 days one way. Send a command, wait 290 days for it to arrive, then wait another 290 days for the response. A round-trip communication would take a year and 8 months. This creates enormous challenges for spacecraft operations. You can't control a spacecraft in real time at those distances. Everything has to be autonomous. The spacecraft has to make its own decisions, navigate on its own, respond to problems on its own. Any communication with Earth would be more like leaving messages for future checking rather than having a conversation. And that's assuming we could even build a spacecraft capable of reaching the Oort Cloud in a reasonable time frame. At Voyager's speed, it takes 300 years just to reach the inner edge. We'd need propulsion systems far more advanced than anything we currently have to do better than that. Some researchers have proposed concepts for interstellar probe spacecraft designed to reach nearby star systems within a human lifetime. These designs typically involve either nuclear propulsion or solar sails pushed by powerful lasers. With such technology, reaching the Oort Cloud could potentially be done in decades rather than centuries. But these remain concepts. We haven't built such a spacecraft yet. The technical challenges are enormous, and the costs would be staggering. Still, I think it's inevitable that eventually, perhaps in the next century, we will send dedicated missions to explore the Oort Cloud. The scientific payoff would be immense, and the allure of exploring this final frontier of our solar system is powerful. When that day comes, when we finally send a spacecraft capable of actively studying the Oort Cloud, it will be one of the great moments in human exploration. We'll be able to see these objects up close, analyze their composition in detail, understand their structure and history. We'll be able to answer questions that right now we can only speculate about. Until then, the Oort Cloud remains distant and mysterious, the ultimate frontier, tantalizingly just out of reach. So if we can't reach the Oort Cloud with current technology, what can we do? How can we study this region and eventually explore it? Let's talk about the future, both near-term observations and longer-term mission concepts. In the near term, our best tool is improved observational astronomy. We can't see most Oort Cloud objects directly, but we can see the comets they send us, and we can potentially detect larger objects if they exist in the inner parts of the cloud. Several upcoming telescopes will significantly improve our ability to detect distant solar system objects. The Vera Rubin Observatory, currently under construction in Chile, will conduct the Legacy Survey of Space and Time LSST. This survey will repeatedly photograph the entire visible sky, detecting anything that moves or changes brightness. It's expected to discover hundreds of thousands of new solar system objects, including many distant ones that might be related to the Oort Cloud. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct infrared surveys that could potentially detect large objects in the inner Oort Cloud. Infrared is particularly useful because objects emit their own infrared radiation based on their temperature. They don't just reflect visible light. Even a very distant object emits some infrared, making it potentially detectable. These observational programs might answer one of the biggest questions about the Oort Cloud. Are there large objects there? If Planet 9 exists, these surveys have a good chance of finding it. If there are other dwarf planets in the inner Oort Cloud, we might detect them too. But observations from Earth or Earth orbit can only tell us so much. To really understand the Oort Cloud, we'll eventually need to go there. Several mission concepts have been proposed over the years, though none have been approved for development yet. One concept is an Oort Cloud probe, a spacecraft designed specifically to reach the inner Oort Cloud within a human lifetime. This would require propulsion significantly more powerful than conventional chemical rockets. The most promising approach is probably nuclear electric propulsion, where a nuclear reactor provides electricity to power ion engines. These engines provide very efficient thrust over long periods, potentially accelerating a spacecraft to speeds much higher than Voyager achieved. With nuclear electric propulsion, a spacecraft might reach the inner Oort Cloud in 50 to 70 years. That's still a long time. Such a mission would be a multi-generational project, planned by one generation of scientists and engineers, executed by their children, and completed by their grandchildren. But it's at least conceivable within the span of a human lifetime. Another concept involves solar sails, large, ultra-thin reflective sheets that catch sunlight and use its pressure for propulsion. While the pressure from sunlight is very weak, it's continuous, and over time it can accelerate a spacecraft to significant speeds. Some designs have proposed using powerful lasers to push solar sails, potentially reaching even higher speeds. The Breakthrough Starshot initiative, funded by Russian-Israeli billionaire Yuri Milner, aims to develop laser-pushed light sails capable of reaching 20% of light speed. At that velocity, a spacecraft could reach the inner Oort Cloud in about 25 years, and the middle of the cloud in about 60 years. However, Starshot faces enormous technical challenges, and it's primarily focused on reaching nearby star systems rather than exploring the Oort Cloud. Still, if such technology were developed, it could revolutionize Oort Cloud exploration. Imagine being able to send dozens or hundreds of small probes throughout the cloud, each carrying sensors to detect and characterize objects, measure magnetic fields, analyze the interstellar medium, and more. We could build a comprehensive map of the cloud, understanding its structure, composition, and population in detail. There's also been discussion of using gravity assists from the Sun itself, a technique called an abirth maneuver. A spacecraft could dive close to the Sun, using its deep gravity well to gain tremendous velocity, then shoot outward at high speed. With careful planning and perhaps a nuclear propulsion stage, such a spacecraft might reach the Oort Cloud faster than any other method currently conceivable. However, all of these concepts face similar challenges. They're expensive, they require technology that doesn't quite exist yet, and they require decades of commitment from space agencies and governments. In an era when space budgets are tight and missions are often cancelled or delayed, getting approval for a Oort Cloud mission is difficult. Still, I'm optimistic. The history of space exploration shows that eventually, we go where we dream of going. We've sent missions to every planet in the solar system. We've landed on asteroids and comets. We've flown through the plumes of Enceladus and studied the atmosphere of Titan. The Oort Cloud is the next logical frontier. When we finally do send a mission there, what will we find? That's impossible to predict with certainty, but we can make educated guesses. We'll find a sparse population of icy bodies, most small but some larger. We'll find pristine material from the early solar system, unchanged since its formation. We might find interstellar interlopers, objects captured from other stellar systems, with exotic compositions. We might find surprises, things we didn't expect, phenomena we hadn't predicted. That's the nature of exploration. Every time we visit a new place in the solar system, we discover something unexpected. Europa's subsurface ocean, Enceladus's water geysers, Pluto's nitrogen glaciers and active geology. Each time, we learn that nature is more creative, more complex, and more interesting than we imagined. The Oort Cloud will be no different. When we get there, we'll make discoveries that reshape our understanding, and those discoveries will raise new questions, inspire new missions, and expand the frontier once again. While we wait for the technology and resources to send dedicated Oort Cloud missions, observational astronomy continues to refine our understanding. This is important to emphasize. We're not just passively waiting. Scientists are actively studying the Oort Cloud right now, using every tool at their disposal. One of the most productive approaches is studying long-period comets in detail. Every comet that visits the inner solar system is a sample from the Oort Cloud, and modern instruments can extract enormous amounts of information from these visitors. Spectroscopy analyzing the light reflected or emitted by comets reveals their composition. We can identify specific molecules in the comet's coma: water, carbon dioxide, carbon monoxide, methane, ammonia, and more complex organic compounds. The ratios of these molecules tell us about the temperature and chemistry of the region where the comet formed. Particularly interesting are isotope ratios. Isotopes are versions of elements with different numbers of neutrons. For example, most hydrogen has one proton and no neutrons, but a small fraction is deuterium hydrogen with one proton and one neutron. The ratio of deuterium to regular hydrogen depends on temperature and chemical processes during formation. By measuring deuterium-to hydrogen ratios in cometary water and comparing them to the same ratios in Earth's oceans, we can test hypotheses about whether Earth's water came from comets. So far, the data is mixed. Some comets have D/H ratios similar to Earth's water, while others don't. This suggests Earth's water might have come from multiple sources, some from comets, some from asteroids, some from the solar nebula itself. We also study the dynamics of long-period comet orbits. By tracking these orbits precisely, we can determine where in the Oort Cloud they originated. Most come from the outer cloud, but some come from closer in. The distribution tells us about the cloud structure and population. Orbital dynamics also reveal information about perturbations. When a comet's orbit doesn't quite match what we expect from pure solar gravity and planetary perturbations, it suggests other forces are at work. These might include outgassing from the comet itself, or they might hint at gravitational influences from undetected objects, possibly including Planet 9, if it exists. Another observational approach involves searching for occultations. An occultation occurs when a solar system object passes in front of a distant star, briefly blocking its light. For very distant, faint objects that we can't see directly, occultations might be our only way to detect them. The challenge is that occultations by Oort Cloud objects are rare and brief. An Oort Cloud object passing in front of a star might block its light for a fraction of a second to a few seconds at most. Detecting this requires monitoring many stars simultaneously with high-speed cameras. Several survey projects are attempting this, and while they've had limited success so far, improving technology makes this approach more viable. There's also the possibility of detecting Oort Cloud objects through their gravitational effects. If a massive object, say, Planet 9 exists in the outer solar system, its gravity affects the orbits of everything around it. By carefully tracking the orbits of known distant objects and looking for unexplained perturbations, we might infer the presence and location of unseen masses. This is actually how Neptune was discovered. In the 1840s, astronomers noticed that Uranus's orbit didn't quite match predictions. Something was perturbing it, calculating where an undiscovered planet would need to be to cause the observed perturbations. Astronomers predicted Neptune's location, and it was subsequently discovered very close to the predicted position. The same technique could potentially find Planet 9 or other large objects in the Oort Cloud, though it's much more challenging. The perturbations would be smaller, and there are many more sources of uncertainty. Still, with enough precise data on enough objects, the technique might work. All of these observational approaches complement each other. Comet studies tell us about composition, orbital dynamics tell us about structure and population. Occultation searches might detect individual objects. Gravitational perturbation studies might reveal large unseen masses. Together, they're gradually building a more complete picture of the Oort Cloud, even without direct spacecraft visits. There's one more fascinating aspect of Oort Cloud astronomy that's worth discussing: its potential relationship to dark matter. Dark matter is one of the great mysteries of modern physics. We know it exists because we see its gravitational effects. Galaxies rotate faster than they should based on visible matter alone. Galaxy clusters hold together despite insufficient visible mass to provide the necessary gravity. And gravitational lensing, the bending of light by gravity, shows more mass than we can see. Whatever dark matter is, it makes up about 85% of the matter in the universe, but we don't know what it's made of. The leading hypothesis is that it has some kind of exotic particle that doesn't interact with light or normal matter except through gravity. Despite decades of searching, we haven't directly detected these particles yet. However, there are alternative hypotheses. One is that at least some dark matter might not be exotic particles, but ordinary matter that's hard to see, things like black holes, brown dwarfs, rogue planets, or clouds of cold gas. These are collectively called MACHOs, massive compact halo objects. Now, here's where the Oort Cloud becomes interesting. The Oort Cloud contains a large amount of mass, perhaps a few Earth masses total, spread over an enormous volume. And it's dark, we can't see it from outside the solar system. An alien astronomer looking at our sun wouldn't see the Oort Cloud at all. They'd see the sun and potentially detect the planets through various techniques, but the Oort Cloud would be invisible. Could there be other Oort Clouds around other stars? Almost certainly. If our solar system formed an Oort Cloud through planetary migration and stellar encounters, the same processes should occur in other stellar systems. This means every star might be surrounded by its own vast cloud of dark, icy objects. If that's true, then a significant fraction of the mass in the galaxy might be tied up in Oort Cloud's ordinary matter, but invisible, contributing to the dark matter problem. Now, before I go too far down this path, I should say that most astronomers don't think Oort Clouds explain dark matter. The mass in Oort Clouds probably isn't sufficient to account for all the missing mass we observe, and there's strong evidence that dark matter has properties inconsistent with ordinary matter, even cold, dark ordinary matter. But the Oort Cloud does contribute to the local dark matter budget. and understanding its mass and distribution helps us understand the total mass distribution in the galaxy. In a sense, every star's Oort cloud is a little bit of dark matter, matter that's there, contributing to gravity, but invisible. There's also been speculation about using the Oort cloud for gravitational lensing studies. Gravitational lensing occurs when a massive object's gravity bends light from a more distant source. Usually we think of this in terms of galaxies or black holes lensing more distant galaxies. But in principle, smaller objects can cause lensing too. It's just much weaker and harder to detect. If a large Oort cloud object, say, a dwarf planet or Planet 9 passed in front of a distant star, it would cause a brief brightening as its gravity focused the star's light toward Earth. Detecting such events requires monitoring millions of stars and having excellent timing. But it's theoretically possible, and some survey projects are designed to detect these microlensing events. So far, no confirmed detections of lensing by Oort cloud objects have been made, but as survey capabilities improve, it's conceivable that we might detect them in the future, providing another way to study the cloud's population. The connection between the Oort cloud and dark matter also reminds us that there is still much we do and understand about the universe. We live in a galaxy filled with mysterious dark matter. We live in a solar system surrounded by a vast, invisible cloud of icy bodies. These two mysteries, one cosmological, one local, both speak to the limits of our knowledge and the frontiers that remain to be explored. We've covered a lot of ground, or rather, a lot of space in this journey. Now I want to step back and really think about what the Oort cloud means for how we understand our place in the universe. Most people, when they think about the solar system, picture the 8 planets orbiting the Sun. Maybe they include the asteroid belt between Mars and Jupiter. Some might remember the Kuiper Belt beyond Neptune. This is the solar system as it's typically taught in schools, as it appears in diagrams and models. But this picture is fundamentally incomplete. The planets, the asteroid belt, even the Kuiper Belt, all of these occupy a tiny region at the center of something vastly larger. Let me try to give you a sense of the true scale. Imagine you're standing at the Sun. Neptune, the most distant planet, orbits at 30 astronomical units, about 2.8 billion miles away. From the Sun, you could see Neptune as a tiny blue dot if you had a good telescope. The Kuiper Belt extends to about 50 astronomical units, still visible, still part of the immediate neighborhood. Now start traveling outward. At 100 astronomical units, Voyager 1's current distance, you've gone twice as far as the Kuiper Belt's edge. The Sun is still the brightest object in the sky, but it's starting to look more like a star than the overwhelming presence we see from Earth. Keep going. At 1,000 astronomical units, you're halfway to the inner edge of the Oort cloud. The Sun looks like a very bright star now, but the planets are long invisible. You're in a region where the Sun's influence is starting to fade. The solar wind is weakening. The temperature is just a few degrees above absolute zero. At 2,000 astronomical units, you've reached the inner Oort cloud. You've traveled 40 times farther from the Sun than the edge of the Kuiper Belt, more than 60 times farther than Neptune. If you could somehow look back at the inner solar system, even with a powerful telescope, you wouldn't see much. The Sun would still be visible, of course, but everything else would be lost in its glare. And you're still not at the real Oort cloud yet, just its inner fringe. Continue outward. 10,000 20,000 50,000 astronomical units. This is the heart of the Oort cloud. Out here, the Sun is just a bright star among other bright stars. It's the brightest star in your sky, but it no longer looks like something special. The temperature is essentially the same as interstellar space, a few degrees above absolute zero. The Sun's gravity still holds you in a lazy orbit, but it takes millions of years to complete one circuit. At 100,000 astronomical units, you're at the outer edge, where the Oort cloud blends into interstellar space. The Sun is still the brightest star, but just barely. Other stars might be almost as bright. You're at the boundary, where the Sun's influence fades and the galaxy's influence begins. Passing stars can perturb your orbit. The galactic tide, the differential gravitational pull from the galaxy as a whole, affects your trajectory. This is the true extent of the solar system, from the Sun out to 100,000 astronomical units, or more, a sphere 200,000 astronomical units across, or about 3 light-years in diameter. Nearly a third of the way to the nearest star. Most of this volume is empty space. The Oort cloud is extraordinarily sparse. But it's all gravitationally bound to the Sun, all part of our solar system, all included in what we should think of as our cosmic neighborhood. Here's another way to visualize it. If the sun were a grain of sand in New York City, Earth would be orbiting about 4 inches away, close enough to see with the naked eye. Neptune would be about 10 feet away across a small room. The Kuiper Belt would extend to maybe 15 feet across a large room, but the Oort Cloud, it would extend 20 miles in every direction, encompassing a sphere that includes parts of New Jersey and Connecticut. That's the scale we're talking about. This realization that the solar system is so much larger than the region we typically think about fundamentally changes how we should think about our cosmic address. We don't live in a solar system that ends at Pluto or even the Kuiper Belt. We live in the center of a vast spherical cloud that extends thousands of times farther. A cloud that contains trillions of objects and represents the true boundary of the sun's domain. Understanding the Oort Cloud also has implications for how we think about life beyond Earth. Not because we expect to find life in the Oort Cloud itself, the conditions there are far too extreme, but because understanding our solar system's architecture helps us understand other solar systems and the possibilities for life elsewhere. First, if our solar system has an Oort Cloud, other solar systems probably do too. Every star with planets likely has its own version of the Oort Cloud, formed through similar processes of planetary migration and gravitational scattering. This means the architecture we've discovered in our rocky planets, giant planets farther out, a debris belt, and a vast outer cloud might be a common pattern. When we detect exoplanets around other stars, we're usually only seeing the inner parts of those systems, the planets close enough to their stars that we can detect them through transits or radial velocity measurements. We can't see their Kuiper belts or Oort clouds, but they're probably there. This has implications for the delivery of water and organic compounds to planets' in habitable zones. Remember, Earth might have received significant water and organic materials from cometary impacts during the late heavy bombardment. If other stellar systems have similar bombardment periods, driven by planetary migration and Oort cloud perturbations, then water and organic delivery might be a common process. This could increase the chances that life develops on planets' in habitable zones. If comets regularly deliver water and organics to rocky planets during their early history, it provides the raw materials for life. It doesn't guarantee life will develop. That requires many other factors, but it makes the possibility more plausible. There's also a more speculative angle. We've talked about how interstellar objects can be captured into the Oort cloud. If this happens in our solar system, it happens in others too. This means there's a potential mechanism for exchanging material between stellar systems over long timescales. Now, the probability of any given object being exchanged is very low, and the timescales involved are enormous, millions or billions of years. But over the lifetime of the galaxy, there's been a lot of time for material to move around. Some researchers have even speculated about panspermia, the idea that life might spread between stellar systems via transfer of biological material on asteroids or comets. I want to be very clear, this is highly speculative. Most scientists don't think panspermia is a likely explanation for the origin of life. Life probably arose independently on Earth through chemical processes. But the Oort cloud and the exchange of material between stellar systems at least makes panspermia conceivable in principle. More concretely, understanding the Oort cloud helps us understand cometary impacts, which have played a major role in shaping planetary surfaces and delivering volatiles to moons' craters. Earth's late heavy bombardment, the resurfacing of icy moons like Europa and Enceladus, all of these phenomena involve impacts. And understanding where impactors come from helps us understand the evolution of these worlds. When we look for life elsewhere in the solar system, in the subsurface oceans of Europa or Enceladus, in the methane lakes of Titan, in the ancient river valleys of Mars, we're looking at worlds that were shaped by impacts, including impacts from Oort cloud objects. The history of these worlds is intimately connected to the history of the Oort cloud. And when we look beyond our solar system, searching for signs of life on exoplanets, understanding our own solar system's architecture, including the Oort cloud, gives us context. It helps us understand what's normal, what's unusual, and what might be conducive to life. We're approaching the end of our journey, but I want to conclude by emphasizing something important. The Oort cloud represents the ultimate frontier of solar system exploration. It's the final unknown territory, our cosmic neighborhood, the last great mystery waiting to be solved. Throughout human history, we've been explorers. We've crossed oceans, climbed mountains, reached the poles, and eventually left Earth altogether. In the space age, we've sent missions to every planet, visited comets and asteroids, and pushed out beyond the edge of the heliosphere into interstellar space. But the Oort Cloud remains untouched. No spacecraft has visited it. No human eyes have seen its objects up close. It exists in our models and calculations, inferred from the comets it sends us, but it remains fundamentally unexplored. This makes it special. In an age where we can look up almost anything on the internet, where satellite imagery shows us every corner of Earth, where our telescopes can peer billions of light years into space and see galaxies forming in the early universe, the Oort Cloud is a reminder that there are still unknowns close to home. There are still frontiers, there are still discoveries waiting to be made. When we eventually send missions therein, I believe we will. What will we find? We'll find ancient ice, preserving chemical signatures from the birth of the solar system. We'll find objects that have never been warmed by the sun, never altered by chemistry or geology, sitting exactly as they were when they formed 4.6 billion years ago. We might find evidence of interstellar visitors, objects captured from other stellar systems, each with its own story to tell about planet formation around different types of stars. We might find larger objects than we expect, dwarf planets or even planets that have remained hidden in the darkness. We'll certainly find surprises. Every time we explore a new place in the solar system, we discover things we didn't expect. The Oort Cloud will be no different. Nature is always more creative, more complex, more interesting than our theories predict. And these discoveries will lead to more questions. What we learn in the Oort Cloud will reshape our understanding of solar system formation, planetary migration, the delivery of water and organics to Earth, and the architecture of planetary systems throughout the galaxy. Each answer will raise new questions, pointing toward new frontiers, new mysteries to investigate. This is how science progresses, not by answering all questions and reaching a final truth, but by continuously expanding the boundary of knowledge, always finding new unknowns beyond what we've just learned. The Oort Cloud embodies this perfectly. It's vast, ancient, mysterious, and full of secrets. It's been there all along, surrounding our solar system, but we're only beginning to understand it. And we won't fully understand it until we go there, until we send our spacecraft, our instruments, and perhaps eventually ourselves to this distant frontier. That day might be decades or even centuries away, but it will come. Human curiosity is too strong, our drive to explore too fundamental. The Oort Cloud is waiting, and eventually will answer its call. So there you have it, the Oort Cloud, the true edge of our solar system. This massive, mysterious region, so far away we've never actually seen it, yet so influential in shaping the history and architecture of our cosmic neighborhood. We've traveled from the familiar territory of the planets out through the Kuiper Belt and into the vast dark expanse of the Oort Cloud. We've learned how it formed through the violent dynamics of planetary migration, how it might contain visitors from other stellar systems, and how it serves as a frozen time capsule preserving conditions from the births of our solar system. We've discussed the comets it sends us, those spectacular visitors that occasionally light up our skies. We've speculated about what else might be out there. Dwarf planets, maybe even larger worlds, hidden in the darkness. We've considered the immense challenges of exploring this region and the future missions that might one day venture there. And we've thought about what the Oort Cloud means for our understanding of our place in the universe. We don't live in a small, tidy solar system that ends at Pluto. We live in the center of something vastly larger, a sphere of icy objects extending nearly a third of the way to the nearest star. The more I learn about the Oort Cloud, the more I realize how much we still don't know about our own solar system. And honestly, I think that's exciting. There are still frontiers to explore, mysteries to solve, discoveries waiting to be made, all within our cosmic backyard. We might not visit the Oort Cloud in our lifetimes, but the fact that it's out there, this vast, ancient repository of icy time capsules, reminds me how much bigger our cosmic home really is, and how much there is left to discover. If you've made it this far through this 90-minute deep dive, thank you. I know this was long, but the Oort Cloud deserves this kind of attention. It's one of the most fascinating and important regions of our solar system, even if it's also the most distant and least understood. If you enjoyed this journey to the edge of everything, I'd really appreciate it if you give this video a like and share it with someone who loves space as much as you do. And if you want to keep exploring the universe with me, make sure you're subscribed. I make deep dives like this regularly, covering everything from planets to stars to galaxies.